Okay, well, thanks for showing up here. As I said earlier, this is one day when it's nice to have the videos, so people can't say they couldn't get the material because their car wouldn't get out of the driveway, which I will hear. We've been talking about identification, and so I want to keep talking about that. What's the big idea behind why are we talking about identification? Okay, again, we're looking at simultaneous equation models. We showed last time that when you have simultaneity, that leads to the standard sort of bias where you get correlation between the right-hand side variable and the error. We said the solution to that, one solution, is to essentially estimate the reduced form, then use the reduced form estimates to recover the structural models. But when we do that, we run into an issue called identification. And so we were trying to understand what this identification issue is all about. And we did it graphically initially. So we had quantity and price, some demand curve. I guess it depended upon income, a supply curve. I think we put rainfall in it. And what we noted is that in order to have identification, in a supply and demand model, more generally we could have 10 equations and it's a little bit different, but it's easy to intuitively understand what's going on in this particular model. Because in order to have identification, you need to be able to trace out each of these curves somehow. So you need something to identify that curve. Because if all we observe are these equilibrium points, all we know is where the 2 points intersect, and we don't know which curve it is that we're getting. And so there's no way to identify one from the other. So somehow we need to sort one from the other. And generally what it takes is you have a variable in the demand curve that's not in the supply curve. Or we have something in the supply curve that's not in the demand curve. Now notice those are exclusion restrictions. Something's left out of some equation. And we'll talk about how to use those exclusion restrictions to just look at an equation and tell if it's identified or not later on, at least the necessary conditions. But in this particular case, as we learned last time, as the demand curve shifts around because income changes, we'll map out the supply curve, and we can use that to tell us what the supply curve is. So all these points, as we connect them, will map out the supply curve. So what two-stage least squares will do, we'll use, or what the procedure will do, is look and say, okay, here's a variable that's unique to the demand curve. When that thing moves, that allows me to figure out what the parameters of the supply curve are. And similarly for this curve, when R moves, it's going to map out the demand curve. So if we want to know what the demand curve looks like, we let this R change. And as R changes, we look in the data for different rainfall years and look at how demand changes. And then that'll give us the demand curve. So we need some unique variable to map out the other variable. Now we could have more than one here, and this could be R and F, fertilizer, if it was a farming application. We'll do that later. So you can put fertilizer in here too. Both of those variables will identify the demand curve. So move it to neither one. As long as they're in here and not in here, then we're fine. Now if a variable appears at both places, it doesn't really help us. So we had demand that depended upon some variable A. I don't know what A is. And S also depends upon A. When A moves, both variables shift, or both curves shift. So it doesn't map out either one of them. It doesn't tell you what either curve looks like. All you get are a bunch of equilibrium points. So if you don't have an exclusion restriction of some sort, something appearing uniquely in one place or the other, you're not going to be able to identify these systems. Mm-hmm.
So each equation has to have at least 2 explanatory variables?
In general, yeah. If you have one would be the endogenous variable,
yeah,
and one would be an exogenous variable. It's not in the other equation. And so we'll have a formula for this in a little bit.
Okay.
But basically it comes down to something like that.
Okay.
Yeah, so you need something unique in each equation. And then we did some examples of each one of these. Our first example was like this one. It didn't even have A. There was nothing unique in either equation, and so we weren't able to identify anything. Then we did a case where one of the two was identified but the other wasn't. Then we did a case where both were identified because we had a unique variable. We did this model last time when we ended. Now I want to put 2 variables into this equation. Oh, actually, we didn't do this one yet. So now we're going to do this one. where we identify both of these. We did models 1 and 2. Did I do a third model last time? Okay. So we'll do a third model. So we only did 2 models, and we only did one where there was no identification. We did one where one of the equations was identified, but not the other. And that was, I didn't write it as model 2 explicitly, but what was the model? Yeah, we put, in the second case, we left R out of here, but we did have investment, so there was nothing unique here, so the demand curve was not identified. But there was something unique here, so the supply curve was identified. Then we went through the mathematics. If you don't get the mathematics, at least try to get the intuition about how you're mapping out one of the 2 curves. Okay. Let me show you another case where both equations are identified. Then we'll do one where they're over-identified, and then we'll move on. Okay. So this is model 3. I don't think I called them model 1 and model 2 before, but this is our third case we've looked at. Q equals alpha naught plus alpha 1, P plus alpha 2, Y. I've been using I there. Let me use I. Plus, what are we using my notes? Doesn't matter. Plus some error U. So that's demand. And it depends upon, this is income and prices. So we'd expect alpha 1 to be negative and alpha 2 to be positive if it's a normal good. And then you have Q equals beta 0 plus beta 1 P plus beta 2 R plus B. So this R is going to identify this, just like we showed over here. This I will identify this. So the way we check identification, and you can do this better with linear algebra by setting this up as a system, but we're not going to do that. But the way we're going to do it, the way we do this is we find the reduced form equations, imagine estimating those, and then see if we can recover the structural parameters. If we can, it's identified. If we can't, it's not. Then we'll come up with a systematic rule so you never have to actually do this. You don't have to actually derive the reduced form and figure out how to go back. But you won't understand what we're doing unless we go through this first. So this isn't something you have to do with every problem, but it's key to understanding what's going on in the background. So what we do first is find the reduced form. So Q and P are endogenous. And then the constant I and R are exogenous. Now, if R and I were in both equations, neither one would be identified. And so it takes something unique in each equation, because you won't map out the other one. That's that case we did with the A thing. It was in both equations. So to get the reduced form, just set this equal. Solve for P. So P equals beta 0 minus alpha 0 over alpha 1 minus beta 1. Alpha 2, alpha 1 minus beta 1. Y, I, beta, plus beta 2 over alpha 1 minus beta 1. R plus E1. E1, some combination of U and V. What would E1 be? It's going to be 1 over alpha 1 minus beta 1 times U minus V, which will get. So when we estimate this, what we'll get is a constant, a coefficient on I, and a coefficient on R, and this is our error. So this is what we'd actually estimate. This is the reduced form model that we'd estimate. And again, the question is, does knowledge of the lambdas and the rho gammas in a second allow us to get back to the alphas and betas? Can we recover the alphas and betas? Now, to get the other solution, you just plug this into, say, this equation, and you'll get that Q equals alpha naught plus alpha 1 lambda 0 plus alpha 1 lambda 1 plus alpha 2 y I plus alpha 1 lambda 2 r plus E2. And when we estimate this, what we'll actually get is gamma 0 plus gamma 1 I plus gamma 2 r plus E2. So gamma 2 is that, so on. So those are the two reduced form equations. Now we estimate those two equations. So we know, so we estimate the reduced form equations. That gives us lambda 0 hat, lambda 1 hat, lambda 2 hat, gamma 0 hat, gamma 1 hat, gamma 2 hat. And did I do that right? Yes. And the question is, can we recover alpha 0, alpha 1? These will be hats, if we use hats here, but I'll not put that in. Beta 0, beta 1, and beta 2. Are they identified? Can we get back to? Because remember, these are the things we're interested in. These are the elasticities of supply and demand. This is the income elasticities and so on. So these are the things you'd actually want to know about. These are what would tell you about whether your theory was right or wrong, give you data about predicting how a change in sales might affect something or a change in rainfall might have, you know. So these are the parameters we actually want to know about, but that's not what we're estimating. We're estimating is lambdas and gammas. So can we get one from the other? And we can in this case. It's pretty easy. Again, if you know, once you've done enough of these, you say, oh, okay. I can see right now that I can get alpha 1 by dividing this by lambda 2. I'll know what this is. I'll have a gamma 2 hat. I'll have a lambda 2 hat. So if I divide one over by the other, I'll get alpha 1. Once I have alpha 1, I can use it here. I'll know lambda 0, then I can get alpha 0. Then once I know alpha 1, I know that, so I'll be able to get alpha 2 from here. So I can get all the alphas, and then once I have the alphas, I can get back here and get the betas. I need one with just one alpha in it. There it is. Or one beta in it. There it is. So once I know alpha 1 and alpha 2, I'll get beta 1 there. And then once I know beta 1, I know those, I can get up beta 0 there. And once I know beta 1, I can get beta 2 there. So the first thing you do is look for one of the things you can isolate all by itself. In this case, you can isolate alpha 1 from this and this. And once you know alpha 1, you're all set. So I'm going to erase this. I don't have to erase that over there. So what you would do in this case is you would say, okay, gamma 2 over lambda 2 is alpha 1 lambda 1, because that's what gamma 2 is over there. See that? Alpha 1 lambda 2 over lambda 2 equals alpha 1. And I know this, so that tells me that this hat over this hat is alpha 1 hat. So alpha 1 hat is just gamma 2 hat over lambda 2 hat, because I know those things from the reduced form. So now I've recovered alpha 1, one of my structural parameters. So the first question you ask is, can I isolate a single parameter with the things I know from my reduced form estimation? I know the lambdas and the gammas, and yeah, I can. Okay, good. Then you look for something that has alpha 0 in it and just one other unknown thing. See, now I know what this quantity right here is. I know this value. That's gamma 0. And I know everything in here but one thing, because I now know alpha 1, I know lambda 0, I know gamma 0. So I can use this equation to isolate alpha 0. So I can say that gamma 0 minus alpha 1, which we've just found, lambda 0, equals what? What's gamma 0 equal? That. If I subtract off alpha 1 gamma 0, what do I get? 0. Alpha 1, yeah. Alpha 0. So this is alpha 0. So that's how I find alpha 0. I know this. I just got that. I know that. So that's what alpha 0 hat is. I'm just using the equation that says that gamma 0, the definition of gamma 0 is alpha 0 plus alpha 1 lambda 0. I know that, and I know that. So alpha 0 is that minus that. So I'm just using this definition right here to get alpha 0. That's the definition. Then it has to be the case that gamma 1 minus alpha 1 lambda 1 equals alpha 2. So I can use that. Now we're just using this equation right here. That gamma 1 equals that. And I know that and that, so I can get that. So this just uses here that this is just the definition of gamma 1 is equal to alpha 1 lambda 1. Let's see that. Plus alpha 2. That's just this definition right here. So that isolates alpha 2. Now I've got the alphas, can I get the betas? What you do here is you go to the other equations and look for a place where there's a beta sitting all alone with a bunch of alphas. Because then there'll only be one unknown thing. Ah, there it is. I know alpha 2, I know alpha 1, I know that. So that equals that. And the only thing I don't know is that. So this one's easy. So now I use that lambda 1 equals alpha 2 over alpha 1 minus beta 1. Then you solve for beta 1. So beta 1 is equal to, what is it equal to? Alpha 1, after you solve that, you'll get that beta 1 is equal to alpha 1 plus alpha 2 over what? Lambda 1. So beta 1 hat is just that. So we just set this, which we know, equal to this. We know the value, but we don't know, we just don't know that term. So we know that, Very equal. I did one thing wrong there. What did I do wrong? It's an easy fix. You won't have to erase. The negative sign over there. I missed that. This equals the minus of that. Then, similarly, now that we know beta 1, okay, good. Here, that equals that. So 10, this equals this. Well, I know that, I know that, I know that, so I can get that. So now you use that lambda 0 equals beta 0 minus alpha 0 over alpha 1 minus beta 1. That gives you that alpha 0 is beta 0 alpha 0 plus lambda 0 times alpha 1 minus beta 1. So we just found beta 1 hat. We know alpha 1 hat. We know lambda. We know alpha 0. So there's beta 0. Then there's one more we haven't used. That's this one. So now we use this one to find beta 2. So lambda 2 hat, which we know is equal to beta 2 over alpha 1 minus beta 1. That tells us that beta 2 is equal to lambda 2 times alpha 1 minus beta 1. Oh yeah, I'll just look at that. We know that, we know that, we know that, so we know that. So after all that, we discover that the model is exactly identified. I'm going to do one more, but I'm not going to go through all the details. I'm going to jump right to the bottom line and show you one more thing, then we'll move along. So I don't have any good way of telling you how to systematically solve this. You either see them or you don't. This is sort of like, you know, if you had trouble with algebra in high school, you're probably going to have trouble with this too. If you didn't, you probably don't. And that's just not something I can solve for you. Fortunately, you're not going to have to do a lot of these. I don't know if I asked you to do any on the homework. But again, we're just saying, okay, we start with a structural model, we estimate the reduced form, that gives us the gammas and the lambdas. Is there a way to use the gammas and the lambdas to uncover the structural parameters? When you look at these enough, you learn how to do it. And I just showed you all the equations that will, in fact, get you back to the structural equations from the data that we know. It requires a recursive process. We sort of find one, and then you use that to find all the others, but you can do it in this case. So this is exactly identical. Now let's do a final model, and again, I'm not going to go through all this. I'm just going to jump right to the bottom line, where we add an extra variable to here. I'm going to add plus beta 3 times fertilizer plus V. Some of you probably think there's enough fertilizer in these problems already. We're going to add more. In this case, once again, we will be able to find all the parameters. It's identified. You can see that because there's unique things in here that will identify this. There's unique things in here that will identify this. This equation is actually over-identified. We have one thing here that identifies it, another thing here that identifies it. Now here's the intuition. Whether you know the math or not, here's the intuition. These could identify different lines. So when F moves, maybe it gives me this demand curve. When R moves, maybe it gives me that demand curve. Which one's right? Essentially what you do is you choose the one that's closest to both. So we sort of choose an average here. But intuitively, all that's going on is you've got two things to identify the same thing. There's nothing that makes them the same. There's an implicit restriction on the reduced forms that we're not imposing that does make these the same, but it doesn't come out of the model. I'll show you that in a second. So if you were to solve this, the way this shows up, so again, you could do the reduced form, P equals beta 0 minus alpha 0 over beta 1 minus alpha 1 minus alpha 2, beta 1 minus alpha 1 I, plus, looks a lot like the last one, beta 1 minus alpha 1 R, plus beta 3 over beta 1 minus alpha 1 f plus E1. And then we'd call that P equals lambda 0 plus lambda 1 I plus lambda 2 R plus lambda 3 F plus E1. So that's your reduced form price equation. Skipping a lot of the details. You just set the two equations equal, solve for P, just like before. So you get exactly the same answer, but one more term, just like we had before. So, then sub that into the other equation to get Q equals alpha 0 plus alpha 1 lambda 1, that's the constant, plus alpha 1 lambda 1 plus alpha 2 times I, plus alpha 1 lambda 2 times R, plus lambda 3 F plus E2. So again, this then becomes Q equals gamma 0 plus gamma 1 I plus gamma 2 R plus gamma 3 F plus E2. So those are the two things that we'd estimate. And so the reduced form estimates will give you then lambda 0 hat, lambda 1 hat, lambda 2 hat, lambda 3 hat, gamma 0 hat, gamma 1 hat, gamma 2 hat, and gamma 3 hat. Okay. And then we take those and we try to recover the structural parameters once again, just like we've done in the first three models. And what happens is, how many unknowns are there? There are alpha 0, alpha 1, alpha 2. How many unknowns are there in this model then? So there's alpha 0, alpha 1, alpha 2, beta 0, beta 1, beta 2, and beta 3, right? So there's 7 unknowns in the model. There's 7 unknown parameters. 1, 2, 3, 4, 5, 6, 7. How many equations do you have? These are your equations. This relates what we know to what we want to know. Well, there's 4 here, right? And there are 4 here as well. That equals that, that equals that. So there's 8 equations. 7 unknowns. When you have more equations than unknowns, what happens? If you have x plus y equals 3, x minus 2y equals 4, 3x minus plus 8y equals 11. Can you solve these uniquely? Unless we got lucky and one's a linear combination of the other two, which shouldn't happen in general, you can't solve these. If you were to plot it in xy space, here's y, here's x, with 2 equations and 2 unknowns, you get an answer. With 3 equations, I get something like this. Do I choose that intersection, that intersection? Which answer do I choose? There's no place, unless one is an exact, if this were 2x minus 4y equals 8, so it's an exact linear combination of the other one, then they'll all hit the same point. But you can't expect that to happen in general. In general, this is what you get when you have more equations than unknowns. There's no unique solution. Do I solve these 2? Do I solve these 2? Do I solve these 2? Which 2 equations do I solve to get the answer? So I'll get 3 different x and y's to solve this, and none will be right or wrong. I'll get 3 different solutions. What we do then is assume that this is from statistical noise. That in reality, we're just picking up noise in the process. They really do go through the same point. So what we're going to do is take the point that's sort of closest to all of them as our estimate. So the solution to this will be the x and y that comes closest to solving all three equations, on the assumption that the only reason why they're not really equal is because of statistical noise in the system. If we didn't have the statistical noise, they'd all be the same. There's an implicit restriction when it's not getting imposed somehow. So when you look at this solution to this, and I'm out of room over here, the way this shows up is you'll get two equations for the same thing. So alpha 1 hat is the slope, right? Or it's 1 over the slope, depending on how I have to think about this, p cubed. It's 1 over the slope. But it's a measure of the slope, right? When you solve the equations, you get alpha 1 hat equals gamma 2 hat over lambda 2 hat, and alpha 1 hat equals gamma 3 hat over lambda 3 hat. So you get gamma 2 over lambda 2 and gamma 3 over lambda 3. And there's nothing that says those are the same. You get two different measures of the slope. So you're over-identified. There's no unique way to go back to the structural model. You have too many equations. If you look at model 3, we had 3 variables. We had exactly the same number of equations as unknowns. There were 6 and 6 in both cases. And so we got exactly the right solution in model 3. This model, we end up with 7 equations, 8 equations and 7 unknowns. So you get an overdetermined system. There's one extra equation. And that extra equation is not necessarily consistent with the others, just like the x plus y thing. And so we'll find implicitly then, there's a restriction that gamma 2 hat over lambda 2 hat has to equal gamma 3 hat over lambda 3 hat. Implicitly, there's a restriction like this that needs to be imposed, but nothing in the estimation imposes it. But this is a nonlinear restriction. But anyway, if this were imposed, you wouldn't have this trouble. But anyway, you get 2 different estimates of alpha 1. What do? We take sort of the average, the one that's closest to both. You actually use a squared norm to find the alpha that's closest to both answers. But basically that's what's going on. So overdetermined systems are sort of harder to work with than exactly identified. So if it's under-identified, you're sunk. You cannot get the structural parameters. If it's exactly identified, great. You can get the structural parameters uniquely. If it's over-identified, that's fine too. You basically have too much information and you have to sort of average it. But too much information is better than not enough. So over-identified is actually better than just identified. You actually have a better system. You just get these inconsistencies that you have to resolve. If you didn't have the over-identified system, you'd take one of these basically as your estimate, where an average is probably better. And so although it makes it a little harder conceptually, you're still better off having an over-determined system. But basically that's identification then. So sometimes under-identified, you can't get back to the structure. You just have to throw up your arms and rewrite your model until you can. Exactly identified, no problems at all. Over-identified, not really a problem, but you run into some inconsistencies that have to be resolved. And we'll talk about how to do this easily. You don't really have to do much but push some buttons to get the estimation to work here. Now, let's come up with a way of determining whether a model is identified or not. So if we have these structural equations, how do we know without actually solving for the reduced form and going through all the stuff I just went through whether the model is identified or not? Turns out there's 2 conditions. There's called an order condition, which is necessary, and there's a rank condition, which is sufficient. The order condition is relatively easy to do, and we're going to do that. The rank condition is not easy to do, and we're probably not going to do that. There's some ways you can do it, but it would take me a whole class to explain it. You put a bunch of zeros and ones, and you look for certain things and certain patterns, and you can get it done. But we'll at least do the order condition. The order condition just checks that you have the right number of variables in the right places, and the rank condition checks that they're distributed in the right way, I guess is the way to say it. So let's let the number of endogenous variables equal G. That's usually the number of equations. How many endogenous variables here? 1, 2. So the order condition, which is necessary but not sufficient. So if this is not true, it's not identified. If it is true, things could still go wrong, but most of the time it will be what it says it is. But it's only a necessary condition. The number of variables excluded from an equation. And we're talking about the structural equations here, not the reduced form. Nothing's reduced from, basically nothing's ever eliminated from the reduced form. But the number of variables excluded from an equation, remember we're talking about having things excluded with a way to identify things, is greater than or equal to G minus 1. That's it. I'll do some examples, show you how this works. What's G in this model? 2. So it has to be greater than or equal to. The number of excluded variables has to be greater than or equal to 1. The variables are Q, P, C, I, R, and F. How many are excluded from this equation? The only thing missing is I. So there's one restriction, one exclusion. I doesn't appear. Q is there. P is there. There's the constant. C is there. R is there. F is there. The only thing missing from this equation is I. Is 1 greater than or equal to 1? Easiest thing I've asked? Yes. And so this is identified. The necessary conditions are satisfied for identification. In this case, it is identified. Yeah, so that's easy. How many are excluded here? So Q's there, P's there, C's there. Two are missing, R and F. 2 is greater than or equal to 1, so it's identified. In fact, because it's 2 is greater than 1, it's over-identified. You can actually tell from the numbers. When the number of excluded things are bigger than G minus 1, it's over-identified. When it's just equal to G minus 1, it's just identified. So in this case, the betas are just identified. There's only one thing missing here. We didn't have any inconsistencies about the betas. They were fine. We had 8 equations and 7 unknowns. There's only one overdetermined thing. Turns out to be alpha 2. And so this one is over-identified. And you can see that here. If it was just identified, we'd only have one equation. We wouldn't have this problem. But it's over-identified. You get 2, you get an extra equation.
Does that order equation apply to a system or each equation?
Each equation within a system. Okay. So, let's do an example. See, what can happen here? These are not different equations. This one, if I multiply this equation by 2, I get this one. So I just divide this by 2, I get back here. So I really only have one equation and 2 unknowns. But it looks like 2 equations. The order condition just looks at each one of these equations and makes sure that maybe there's a z and a w somewhere. This is w plus and this is z plus. So this one has w missing and this has z missing or something like that. But it just looks at the two equations and makes sure you have the right exclusion restrictions. It doesn't check the rank of the matrix. If I were to write this in matrix form, the rank of the matrix would only be 1 rather than 2. That tells me how many independent relationships I have. So the rank condition is really telling me whether or not I have the right information in the right places, whether I have the right number of, whether the equations are linearly dependent or not. Turns out that's kind of hard to check in general with a great big system. But the order condition is just making sure that each equation has the right things missing, but it's not checking to see if you have each equation is related to the other in some systematic way. And that's what the rank condition is going to do for us. So when there's two independent equations, we say the rank equals 2, and that's what we want. We want at least a rank of 2. If the rank is only 1, which means there's only one independent equation, then it's not identified. And so even if you have the right exclusions in this system, it's not going to be identified. All right, here's an example. Easy, I think. y1 equals, so this is a system of structural equations. X's are exogenous, Y's are endogenous. So that's the first equation of our system. Maybe this is income, consumption, interest rates, things like that. Whatever. Oh, it got sucked up in the void. I don't know. It's a mistake in my notes. Thank you. Should I change it or leave it? Will it confuse you later not to have it? It probably will be confusing not to have an alpha 3 there. You'll think there's an exclusion restriction that isn't present. Let me make sure there's not an x3 in this damn thing. Yeah, that's right. Thank you. Sorry about that. So there's going to be 3 equations, 3 endogenous variables. This one's beta 0 plus beta 1 y3 plus beta 2 x1 plus b2 and oh no. Figure if I bring 2 cups to class, you'd talk about me. So what are the variables in the system? y1, y2, y3, c, x1, x2. The endogenous variables are the y's. So this tells us that g minus 1 equals 2.
Where's c?
The constant. It doesn't change. It doesn't really identify things. I don't want to get into that. So I'm just going to put a constant in all your problems. Or leave it out at all. That way I don't have to deal with it. Constant's a little bit different. You need something that moves to identify the other stuff. And C never moves, so it doesn't really count. But I'm just going to abstract from that. So I'll make sure your problems don't have to worry about that. Okay, so how many are excluded here? Sometimes 0 is the right answer. Is there anything included here? So that's not identified. So the first equation is not ID. What's left out of here? I see no y2. And there is no x2. Or y1, yeah, thanks. So, 2? 2 things missing? And g minus 1 is 2, so this one is exact. Yeah, this is hard, isn't it? Like this? Easier than all that algebra we were doing to do the identification? I think it is. What about this one? Yeah. Obviously, I wanted an example. So if this was a multiple choice test, okay, he wanted an example of all 3 cases. This one must be over-identified. And you would be right. But why? Because you've excluded y1, x1, x2, 3 things gone. G minus 1 is 2, so this one's over-identified. There's 1 extra restriction for this model. This shifting around will identify this, and this shifting around will identify this. And so, okay. Got it? Estimation. How do you estimate this? So we're first going to talk about indirect least squares. Then we're going to say we're not going to use indirect least squares, but it helps us understand two-stage least squares. So the first is what's called indirect, so estimation. ILS. That's how it's usually. Now the problem with this is it works only if model is exactly identified. So it's not general enough for our tastes. We'd rather have something that works always. This doesn't. But it does point to the procedure. So let's illustrate this CT. We've been doing this. So endogenous going to be Y, income and consumption, and exogenous will be the constant. I've already used C for consumption. Oops. That's not the constant, that's consumption. The constant and investment. So, do we, is there anything to estimate here? See any parameters? So I could care less, couldn't care less, whether this is identified or not, because I don't have any parameters to estimate. So we don't worry about this question. About this one. What's missing? I. How many endogenous variables? 2. G minus 1 is 1. 1 is greater than or equal to 1. There's one thing missing here. There's no I in this equation. There's no I. All this part's included. There's no I in T. So it's exactly identified, so we can use indirect least squares. So what you do is you write down the reduced form, estimate the reduced form, and recover the structure. So for indirect least squares, you do just exactly what we've been describing the whole time. You find the reduced form. CT is alpha over 1 minus beta plus beta over 1 minus beta IT plus UT over 1 minus beta. YT is alpha over 1 minus beta plus 1 over 1 minus beta IT plus UT over 1 minus beta. What's that? It's a multiplier. 1 over 1 minus the MPC. So we could estimate, you could actually use either equation. Let's estimate CT is lambda 0 plus lambda 1 IT plus PT. So we're estimating this equation. You could estimate this one too. It wouldn't make any difference. You can get the beta out of either one. Once you have beta, you can get alpha here. So estimate this. You're going to know lambda 1 and lambda 0. So that gives you lambda 0 hat, lambda 1 hat. Then beta hat, using the fact that that equals that, is lambda 1 hat over 1 plus lambda 1 hat. And alpha hat is lambda 0 hat over 1 minus beta hat. So you have your estimates of your structural parameters. So your multiplier estimate, if you're interested in the multiplier, 1 over 1 minus b, you can get it from this. You get b back here. And this is a weird case because either equation will identify things. You could run either one. Now that won't work in the general case. So ILS is rarely used because it won't work when you have over-identified. And if there's a lot of equations, it's pretty dang tedious. It was easy to work this out for this case, but you saw just in a very simple supply and demand system earlier how hard it is to go back to the structural models. When you write down 10 equations and 10 unknowns, solving that back for the structural parameters, even if it's exactly identified, would not be an easy or a fun job. Though something like Mathematica would do it in an instant. So if you know how to program, it's not that bad. But why bother if there's another easier way to do it? So let's look at an instrumental variables procedure as an alternative. This will work whether or not it's over ID'd or not. And even better, when it's exactly identified, it's equivalent to ILS. And so this gives you the same answers as ILS when it's exactly identified, and it works when it's over-identified. So why do ILS for the one case when this is easier? It's much easier to do this than it is to do that, and it works and gives you the same answers. So, and a special case of this instrumental variables procedure is what's called two-stage least squares. And that's what we're going to actually be doing. But let me explain this. Let's start with an example. Y1 is alpha 1 y2 plus alpha 2 x1 plus u. Y2 is beta 1 y1 plus beta 2 x2, I hope, yes, plus v. This is exactly identified because I'm missing an x2 and missing an x1, and g minus 1 is 1. And so, yeah, this is exactly identified. So we could use ILS here, but we're going to do something else instead. Now, what's the problem with this system? Suppose we try to do OLS on this. So suppose we try OLS on the first equation. What's the problem? We already talked about this quite a bit. The problem is that y2 is correlated with u, the error. So y2 is correlated with u. How do we know that? We know that because from this equation tells us that y2 is a function of y1, right? And this equation tells us that y1 is a function of u. So it must be that y2 is some function of u. Maybe that's too mathematical. In words, y1's in y2, and u's in y1. So u must be in y2. If u's in there, it's correlated. It's a simultaneity. So OLS won't work, but we know how to solve this problem. We know how to solve this. We can use instrumental variables. So what do we need? We need a variable that is correlated with y2, but uncorrelated with the error term. And there's a variable staring at us in the face that's not part of this equation that's correlated with y2. It's x2. When x2 goes up, what happens to y2? It goes up, right? If beta 2 is positive. So these are correlated. And x2 is exogenous, so it's uncorrelated with the error term. So we can use x2 as an instrumental variable for y1. Estimate by IV, and we're done. And we get the ILS answers. So you can show that. And if this were my PhD students, I'd make you show it. But we won't. So, yeah, let's do that. So, when I break chalk, when the right-hand side variable is correlated with the error, one answer is IV estimation. Not a very good N in the word answer there. You know what it says. But what to use as IV for y1, for y2? Because that's the problem. y2 is correlated with the error term. What do we use as an instrumental variable here? Use x2. Why? Second equation shows that y2 and x2 are correlated and x2 is uncorrelated with error since it's exogenous. So, solution is IV estimation with x2 used as IV for y2. And I don't think we'll actually write out the instrumental variables estimate.
So in practice, we never actually have to do the identification problem work. We would just use instrumental variables again.
You would check to see if that's identified using the G-1 thing.
Yeah.
Once you find that's identified, you estimate with instrumental variables.
So like the past 2 days, just so we understand it.
Just so you understand it. That's what I've been telling you the whole time, is we're going to get to a point where you don't actually have to do this. But to really understand what the identification problem means, I had to go through all that, sort of show you the underlying mechanics, so this doesn't really sink in. That's my view.
Because this would take like 20 seconds to use, right?
Exactly. That's what I was saying. The estimation part of this part of the course is very, 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 very easy. The hard part here is conceptual. Heteroscedasticity, I think the conceptual part wasn't that hard. You just divide by the variance and weight things right. But the actual estimation was really tedious and hard. So we've sort of flipped roles here. Yeah. But there's no way to really explain identification without sort of writing out those initial models and showing it explicitly. Now, let's do a harder case for IV. So let me change it to just add a beta 3x3 here. This equation is now over-identified. Oh, wait. That's not right. This is now over-identified. Because it's missing x2 and x3. There's 2 exclusions, and G-1 is only 1. This one's only missing one thing. It's missing x1, or this one's exactly identified. We kind of, the exact identification, here what would you use for an instrument for y1? Suppose I want to estimate this equation. Well, I've got the same problem. This is correlated to this through this equation. So what would I use as an instrument? Oh, well, x1 is correlated with y1. It's not part of this equation. So I can use x1 as an instrument for this variable. Now let's go, what if I want to estimate this one? Well, now it's a little bit different because I have 2 instruments. So the first equation has y2 correlated with u, just like before. What to use as instruments? Well, there's 2 potential instruments here. x2 is certainly correlated with y2, and it's not in this equation. x3 is certainly correlated with y2, and it's not in this equation. So x2 and x3 are both potential instrumental variables. Which one should you use? Turns out what you use is a linear combination of the two, and we'll talk about how to get that soon. What you would use for an instrument in this case is some linear combination of x2 and x3. So you would use ax2 plus bx3 as the instrumental variable. But how do you choose A and B? And we'll talk about that next. So the best instrument here is some linear combination with A and B chosen in a particular way. Now practically what you do is exactly what you did for instrumental variables. You just write the first equation out. You have that second box. You put your instruments in there and everything works. But we want to understand what's going on in the background. That's the two-stage least procedure. So somehow we need to get this linear combination. This is where two-stage least squares comes in. So this is where two-stage least squares comes in. The first stage gives us our instrument. The second stage, we use the instrument to do the estimation. So the first stage, we're going to get this linear combination of the two instruments. In the second stage, we'll estimate the model. So we'll find an instrument for this. Then the second stage is, the first stage is finding that instrument. The second stage is estimating by IV. The computer does all this automatically. Okay, so what's going on? Got another example here. Unfortunately, I don't really need another example. So let's use a different example to illustrate. It's basically this example, but I want to go back to, this is going to be Q, P, R, and F, Q, P, and I. It's really the same example, but I want to connect it to what we've been doing already, just because I thought it'd be more intuitive. So it's exactly the same example, except for the Y1 and Y2 are essentially reversed here. That's the only real difference. But it's essentially the same system that we're using. So let's go back to this. Q equals alpha 0 plus alpha 1p plus alpha 2i plus u. And Q equals beta 0 plus beta 1p plus beta 2r plus beta 3f plus v. That's our model. It's really just that model that I wanted to go back to the things we're more used to. Somehow getting the names seems to help. Okay, stage one of two-stage least squares. You estimate the reduced form equations. So you estimate, you regress each endogenous variable on all the exogenous variables in the system. This is just the reduced form equations, because that's what the reduced form equations are. The endogenous is a function of the exogenous, and all the exogenuses usually appear in all the equations. So you just estimate p hat equals lambda 0 hat plus lambda 1 hat I plus lambda 2 hat R plus lambda 3 hat F plus, well, there's no error because I'm using the estimated. And then Q hat equals gamma 0 hat plus gamma 1 hat I plus gamma 2 hat R plus gamma 3 hat F. These are the IVs. This is the A and the B that we were talking about over here. Here's A and B. So these are the instrumental variables. Why does it work? Let me let you catch up and then I'll tell you. Yeah, it's 9 minutes. I'm watching too. One of those days. P hat is a linear combination of all the exogenous variables. So it does not depend upon the y's, it only depends upon the x's. So this does not have any problem of being correlated with the error. This is purely exogenous terms. So this is a linear combination of the exogenous variables. AX2 plus BX3 plus CX4. It's just the x's. It's just the exogenous things. So this is exogenous. It's no longer correlated with the error. We've stripped out the correlation part. Same here. This is purely exogenous. So what we've done is just taken each of these equations. When you solve the reduced form here, P, these are the reduced form solutions. So P depends upon I, R, and F. So P depends upon I, R, and F. So you just take the exogenous part of this. You leave out the V thing and just put in the exogenous part. You're essentially putting in that part of the equation and solve this. It'll only depend upon exogenous things. So you're saying that Q is, this equation here, you're saying, well, Q is correlated with I, R, and F through this equation. So when I write in the reduced form, I'm just stripping it of the P part. I'm stripping it of the endogenous part. I didn't say that very well at all. I kind of confused myself with that statement. Okay, let me start over. How do we want to say this? The problem with Q, the problem with P in this case, it's harder to see because you don't have, when you solve the reduced form and do the error, there'll be a U and a V in it here. And so the solution for P will have the U and the V in it. We want to get rid of that U and that V. And the way we do it is we just take this linear combination of purely exogenous things. So we're taking this variable that has U in it through the other equation, and we're stripping out the U by writing this regression and just making it purely a function of exogenous things. So then we have a valid instrument. And if you look at this system, you know that Q is correlated with all the exogenous variables in the system. So it's going to work as a valid instrument. If I wanted to know what to regress Y2 on here, so say I want to run this, I want to get an instrument for Y2. And I want it just to depend upon the exogenous variable. So I ask myself, okay, what does Y2 depend upon? Okay, well, from here I can see Y2 depends on X2 and X3. So those are certainly instruments. But also, through Y1, it depends upon X1. So X1 is also a valid instrument. So Y2 is correlated with X1, X2, and X3, so I'll just regress it on those things, on all the exogenous variables in the system. if I want an instrument for y2, I get the same, for y1, I get the same thing. Well, y1's a function of x1 through here, but also through this equation, it's a function of x2 and x3. So if I want to get an instrument, I should run it on all the things that it's correlated with, which is all the exogenous variables. And so the way these systems work is that you always just take the things here and regress it on all the exogenous variables. In general, these things, because it pulls in the other equations through the endogenous variables, will depend upon all the x's in the system. So you just run the y's on the x's, form your instrument, and the second step is just to, stage 2 is really simple here. You just run the instrumental variables regression. So stage 2 is use p hat and q hat as IPs. Now, I am not convinced you understand the logic here, and I haven't done the I haven't explained it well enough, I don't think. So I need to start with another example next time, go through it one more time again, and sort of give you the idea of why you run the instruments this way, what's going on. We'll do this one more time and try to get it. So I'll start there next time. We're basically done with this chapter. Then I'm going to go on to chapter 10 on qualitative and limited dependent variables. We're essentially done with this chapter now, but I don't think that leaving it here, the ends aren't tied up yet, so I need to come back and do this one more time.